Hello, this is a continuing series of videos on how to add vectors. We first did a video on how to add two vectors just in terms of drawing, graphing, and that sort of thing, but with no math. Then we did another video, another really short one, where we actually learned how to subtract vectors again by drawing with no math. Now I'm going to do what I call the world's best physics, or excuse me, what I call the world's best vector addition problem, and I'll explain to you why I call it that in a second. But anyways, we're going to start off by sharing my screen, and then I'm going to show you how to do a vector addition problem graphically. In other words, just using Protractor and a scale and a ruler. And then once I have established that scale and done the drawing, I can actually measure it to find out what the resultant is. And then I'm going to do the vector addition with actual component methods using trigonometry and stuff like that. So let's start by sharing my screen. So this is what I call the world's greatest vector addition problem. You can actually get a download of this document if you'd like. You just have to send me an email at billy@PhysicsSolutions.com and just put world's greatest vector addition problem as a subject line, and I'll email you the document or email you access to the document. The question is, what is the sum or resultant? Two words that mean the same thing in vector addition. What is the sum or resultant of the following vectors? The reason why I call this a couple of reasons that I consider this the world's greatest vector addition problem, which obviously is a little bit of hyperbole, is that I'm using all the different types of notation that you could use to specify an actual vector. Specifically, I'm using just an at symbol, which normally you could say the vector A is 14.14 newtons directed at 45 degrees. I just use the symbol at just to direct that. And what that means is when if I don't give any other specification, or someone doesn't give any other specification, like compass heading or south of east or something like that, then that just means you're supposed to assume that's a 45-degree angle measured counterclockwise from the positive x-axis upward. That's what I mean by counterclockwise. If it was negative, you'd actually measure from the positive x-axis in a clockwise direction or downward. That's sort of the easiest notation, but it is what we call polar notation. Another one, the other vector B is 20.00 newtons at 30 degrees south of east, which is also called negative 30 degrees. So in a normal coordinate system, your y-axis is supposed to be, as far as a compass heading, your y-axis is supposed to be the northern direction, and that would be 0 on a compass, and then your east is the positive x-axis, which is supposed to be 90 degrees, and then of course south would be 180, and west would be 270. Now, the other thing that makes this the world's greatest vector addition problem is I'm using only special angles. I'm using the 45-45 triangle and the 30-60 triangle and the 3-4-5 triangle. So we can actually do all this without actually having to do any trig calculations. I mean, we'll still be doing trig calculations, but we won't have to actually use trig functions on our calculator if we know our special angles. Vector C is 25.00 newtons at 53.1 degrees west of north. So those terminologies will mean more to you after you've seen this, if they don't already mean something to you now. And then finally, D is 40.00 newtons at a compass heading of 240 degrees. So we're talking compass heading, not the measured counterclockwise from the positive x-axis. The compass heading is actually measured clockwise from the positive y-axis, which is considered due north, and 0 degrees. So now that you've seen the actual problem, we're going to try to actually let you guys see how it's done, first graphically and then mathematically. So let me stop sharing my screen. And we're going to go from here. I'm going to actually do my document cam. So you can see I've got the coordinate systems drawn already. As I told you, north is the positive y-axis direction, and it's also north 0 degrees by compass. The x-axis is to the right, and that's the eastern direction according to the compass, and that would be 90 degrees. Whereas if you're actually measuring the angles, like the first one I said was 14.14 at 45 degrees, what I mean is you rotate from this positive x-axis counterclockwise until you reach 45 degrees. And using a protractor, you actually mark that line, and then you use your scale to actually make the size appropriate. So that's what we're going to do now. So the first vector on this was in fact 14.14 newtons at 45 degrees. So that might sound a little scary or whatever, but in fact it's I'm able to do this without even a really that decent of a protractor. I have a protractor that's only measured in the nearest 5 degrees, but I'm going to do it with it and estimate, 1, 2, 3 degrees, that sort of thing. But the 45 is pretty straightforward, since that's actually marked at 5 degree increments. So all I have to do is remember the center of your protractor will have some kind of hole or some kind of arrows pointing to it, and basically a line should emanate from that center and run to the 0, 180, and into the others 180, 0. So what you have to do is kind of be a little persnickety about it and try to get it just right. So I'm like standing up and looking over to make sure everything's lined up properly. I see that the 0 is right on the center of my x-axis. I see that the center of my coordinate system, my origin, is on. It looks like it's perfectly dead center in this hole, so I'm going with it. So I'm going to mark right here, and the farther you mark away, the less a little error. So if I did in here, a small error would be a bigger deal than if I marked out here. Now a small error out here is going to be less of a deal because it's so much further away. So I know that's the line along which my very first vector, the A vector, is going to be pointed, and I know it comes from the origin out there. And really all that matters is that I get the length right in the right direction. So I'll draw this pencil line for starters, just to give me what I'm doing. What I decided to do was to actually do a scale that is basically 2 centimeters equals 10 newtons. So my scale is 2.00 centimeters equals 10 newtons. So when I do a vector that's 14.14 newtons, I divide that by 10, that's 1.414. Then I multiply that by 2. It's just like a unit conversion, so I multiply that by 2, and I end up getting 2.828. So now what I do is go over here and try to mark off the distance in centimeters of 2.828. Again, I try to stand up so I make sure I don't get any parallax or anything funny like that. And I estimate what is roughly 2.828. So I'd say that's roughly 2.8, 2.82, maybe be right there. So now I know where the end of the vector is. And this one's not along any axis, so I'm just going to draw it black. Again, the point where that ends is most important. That's why I didn't care about doing a straight edge, because I've got the line already established. So this angle is 45 degrees. Now the next one is vector B, and that's supposed to be 20 newtons. So this one was 14.14. The next one is supposed to be 20 newtons at 30 degrees, but it says 30 degrees south of east. So I really need to go horizontal and then go down 30 degrees like that. So at this point, what we want to do is we want to set up another coordinate system, just like the one before. I want to make sure my y-axis is, of course, perfectly vertical, and then I want to make sure my x-axis is perfectly horizontal. In this case, I really only need the x-axis because I'm measuring at 30 degrees south of east. So the east is the horizontal direction, the x-axis in other words. So I just draw that right there, and now I have enough to make a coordinate system correct. So again, I make sure that I line the center of the circle, the center of the protractor up with the end of the vector, and I make sure the 0 is lined up with what I think is the x-axis. And in this case, I'm going down to 30 degrees, which is over here. And again, I choose the farthest distance in case I make a little error. It won't matter as much. So now I'm just going to connect these two spots, and I know that the new vector will lie along this line. By the way, I've done this a couple of times just to make sure I had all the sizes right, so I knew where I was drawing it was going to work out right. So I know this vector is going to be along this line. It again is not along any x or y axis, so I'm just going to color it black. And its magnitude is 20 newtons. So according to our scale, that's you have to divide 20 newtons by 10. That gives you 2, and then multiply it by 2 centimeters. That gives me 4. So I need to do a 4 centimeter vector. So again, I stand over top, make sure I'm not getting any parallax, and I try to make this mark perfectly right on the flat 4. That looks pretty good. So now what I'm going to do is draw the head of my vector like so. And then of course I can just draw the vector along there if I wanted. Again, this straight edge is not critical here, so I really should have done it probably just for neatness, but it's not critical because of that right there. So that looks pretty good. Now all we have to do is do another coordinate system right at the head of this vector. So the next vector is 25 newtons at 53.1 degrees west of north. So this time it'd be better to draw the north axis. So I'm going to use the straight edge here to get a lined up on what's vertical. So I'm using the corner part here to make horizontal. I know this is a 90-degree angle. So if I draw right here, that should be vertical and that should be my north. And my C vector is 25.00 newtons, 53.1 degrees west of north. So that means that way. Okay. I should probably go ahead, now that I roughly know where everything is, I should go ahead and mark this as 30 degrees. I'll actually do it like this because I think I'm going to run into some problems otherwise. That one's 30 degrees, and this one was, of course, 20.00 newtons. So that's vector B. Now I'm going to take my protractor again, and this time I'm going to measure 53.1 degrees west of north. So I can just put the center of the circle at the end of the last vector. Again, making sure the center of the protractor lines up right at the end of the vector, and then making sure the 0 line is on north. Now here's where I'm going to have to estimate because my protractor only comes in 5s. So that's clearly 50 degrees up from there. There's 55. So I'm going to say 53.1 is maybe roughly there. Obviously, that's not very good, and I probably should do it out here a little better. That way, if I do make a little error, it won't be as big a deal. So I'll put it out there. And now I'm going to draw a vector right along that line, but from the end of the last vector through that second dot that I put. And it should be about like that. Hopefully I drew it long enough. If not, I'll have to draw another, but that's not a big deal. Now, this vector is supposed to be 25 newtons. So if I divide that by 10, I get 2.5, and then I multiply that by 2, I get 5. So this one should be 5 centimeters in length. Again, trying to stand up above it, make sure I don't make any careless parallax errors or anything like that. I put the 5 on it. And now I'm marking right here as the end of the vector. So again, this one's not along any axis. Since my other one looks so bad, I'm going to go ahead and actually let me double check that measurement. Since I have a dot nearby, I don't want to do the wrong measurement. So I'll put it in pen this time just to be safe. So I'm going to put this on 5 again. The end of the vector at 5. Yeah, I was definitely going to hit the wrong mark. So that end right there is all that matters for the vector. So to be careful, I will go ahead and trace that line, make it look a little better. Back to here. Okay. So it should actually be right there on that dot. Now that's my vector that was 25.0 newtons. And that in fact was at 53.1 degrees. This will all help me when I go to decide whether the individual components are positive or negative. So now I need to draw the last vector, which is a compass heading of 240. So 240 would be 0, 90, 180, and then another 60. So really I need a south axis for this one. So I'm just going to draw a vertical line south of where the end of that vector is, which is right about there. And obviously you can tell there's a little bit of error where my pen made a big fat blob. So that's obviously introducing some error, but you'll be surprised. I'll probably get a very low error on this compared to the mathematical calculation, which is the correct one. So that's due south. I need to go 60 degrees beyond that way. So now all I gotta do is set up my compass again, being careful to put it in the right place, and so on and so forth. So I'm gonna do it like so. Put the 0 right at the end of the vector, make sure the zeros are, make the center of the compass circle right at the end of the vector, which I think is right there. Make sure the 0 is on the line. I did that. Now I want to go 60 degrees up here. So that happens to be marked right there. So that's a pretty good mark. Now all I have to do is connect the end of that vector to this spot, and that'll be the line along which the vector lies. Now this vector happens to be kind of long, so I'm gonna make sure I extend it a good ways. That looks to me like I did hit the end of the vector where it was supposed to be. So now in this case, it's 40 newtons. So 40 has to be divided by 10. That makes it 4, and then I gotta multiply that by 2. So I gotta go a full 8 centimeters on this one. My right angle device does actually go up to 8 centimeters. So I'm gonna go ahead and make sure I've got it upside down so the beveled edge gives me a little gap off the paper. And there's my end of my axis, right about there. So I am saying the end of the vector should be right there. So now I'm going to draw again a black vector because clearly this is not along one of the axes, so I haven't made it up into components yet. So I'm going to say that's the end of my vector. And now I'll draw in the rest with a straight edge to make it look a little better than that first two did. So those are some of our 4 vectors. Goes from where the first one started to where the last one ended. So now I can go ahead and draw that. That one I'm going to do in green just because it happens to be the solution. And I'm not using those colors for any particular coordinate direction. So if I make it green, it'll be easy to stand out which one's which and that sort of thing. So our resultant vector is actually this guy right here, which I can measure. And this one turns out to me to be what I would call, it's actually close enough, otherwise I'd extend it a little further down here. But looking at this, making sure everything lines up, this looks to me to be right about 9 degrees. So I'm going to say this answer is 9 degrees, which is also the same thing as saying 189 degrees. If I just wanted to say an angle, this angle would be counterclockwise from the positive x-axis. It'd be 180 to there, so it'd be 189 degrees. And now, if I want to measure the actual length, I'm going to call this roughly 5.51 centimeters. Of course, I got to convert that back to the scale that we had. Oh, and I forgot to mark this one. This one was 40.00 newtons at 60 degrees from there. Okay. So according to just this graphical analysis, which cost us nothing but a protractor and a little bit of time, our resultant vector R, notice I didn't put a vector symbol over there, so that's fine to call that R. Our resultant vector R would equal 5.51 centimeters times 10.00 newtons over 2.00 centimeters. In other words, I use any number of sig figs that I want. try to focus that a little better. When I multiply those two numbers, I get 27.55 newtons. And I want to say R, the resultant vector, is equal to 27.55 newtons at 189 degrees. I can't estimate beyond a whole number, and even a whole number was sketchy at best, but that's what I got graphically. So I'll put a little G on that just to remind everybody that that was via graphical analysis, not the mathematics. So if I want to actually go ahead and do the mathematics, what I need to do is break up each of these into X and Y components. So I have to have an X component for this vector, a Y component for this vector, an X component for this vector, a Y component for this vector, so on and so forth. So let me go ahead and draw those so I can get an idea of what direction they're going to be pointing. So the Y vector, the Y component of the vector A is of course going to be vertical, because the y-axis is vertical, and it's going to be right there. It's going to be pointing upward, so I drew it red. And the x-axis is going to be pointing to the right, so I'm going to draw it red, or I should have drawn that blue. Do stupid me. My system is blue for positive and red for negative, and I ended up drawing it the wrong way. So here's a blue x component as well, so that should also be positive, like that. That's vector A. This one's vector B, whereas this one's vector C. Okay, but we can see vector B has a negative x component. So this one I should actually draw negative. I could use that same line, in fact, for the y component of B. And then, of course, I can see the x component of B is going to be positive. So it'll be right there. Now you can also see that the y component of vector C is going to be positive. And the x component is actually going to be negative. So I'll draw the x component first, right here. And I'll draw the y component right here. And I can see that's positive, like I said. And then finally, I can draw the y component of vector D, which I should label right over here with D. I can draw the y component. It's basically going to be straight down here, and it looks like it hits right on that line. It is a negative y component, so I'm going to draw it red. And it looks like it hits right on that last line, but we're just doing this to keep track of our signs more so than actually doing accurate measures of them. And of course, the y-axis, so the y coordinate, is also negative, so I want to draw that red as well. So that's my vector, that's my d sub c, or d sub x, excuse me. This is my d sub y. Obviously, this guy was my a sub x, and this is my a sub y. This is my b sub y, and this is my b sub x. This is my c sub y, and this is my c sub x. So we've now got all our components labeled, and we should be able to make some sense out of that. So now that we have all of that, I want to move up where we can probably still see the individual vectors and their components, but we aren't going to be able to see the north and all that stuff, but I think I can still fit everything else in. So what I really need to do is I need to convert the A vector into like an IJK type vector, in other words, X components and Y components. So if I look at this vector, I think I can make all that out. So the vector A sub x is going to become, I basically need to take this part, which is, if I take the cosine of this, I'll do cosine equals a sub x over a. And of course, we knew a was actually 14.14, which you might notice is 10 times the square root of 2. And then I got to multiply that by cosine 45. So I think you can automatically tell. Notice it is positive, so I'm forcing that sign on there. And that's sort of the way you have to do it when you just randomly take any angles instead of consistently pulling one from the counterclockwise from the positive x-axis. When I do that, I'm going to get 10.00 newtons, and a sub y is, this time if I take the sine of 45, I get a sub y over a. So this will be, and again it's positive, so this will be positive 14.14 newtons times the sine of 45 degrees. Again, it's a special triangle, so I really don't have to even pull out my calculator. I know that's going to get 10, but by all means, you guys should be using your calculator. So another way I could have written A instead of this polar type way that I did, I could have wrote A as 10.00 newtons I hat plus 10.00 newtons j hat. Similarly, for vector B, I can do B sub x. Now, B sub x is this component right here. I've got this angle right here. So if I take the sine, I get the bx over the hypotenuse, which is the magnitude, which is 20 newtons. So the x component is going to be given by sine when I use that angle up there, that 30-degree angle. Oh, excuse me, that 30-degree angle is this one down here. Sorry about that. Okay, it was measured down this way. If I want to pull it in this triangle, it's going to have to be this angle over here. So this is the actual 30-degree angle, in which case the sine of 30 gives me by, negative of by actually, over the hypotenuse, and the cosine of 30 gives me bx times the cosine times b. So now I'll take bx. Bx is going to be 20 times cosine 30. And again, that is actually a positive direction, so I'm forcing that. And that tells me, of course, the special triangle, this being 20 newtons is actually 10 times 2, which was normally the 30-60 triangle. So this should be 10 times the one that's adjacent to the 30-degree angle. So that should give me positive 17.32 newtons. And that's basically 10 times the square root of 3, because square root of 3 is roughly 1.732. B sub y is equal to 20.00 newtons, but notice B sub y is negative, so I got to force that sign right there. And this one's going to be times the sine of 30 degrees. And of course, the sine of 30 degrees is going to give me that opposite one. And of course, that one was the square root of 3. This one's going to actually be 1. So I'm actually going to get 10 times 1 are negative 10.00 newtons for this component. And I could actually say that B is equal to 17.32. Notice I'm using a different notation here. And negative 10. So again, this is another case where I'm talking about this is the world's greatest problem, because now I've shown you an I hat and a J hat notation, as well as an alternative notation where you do like a coordinate, but instead of using parenthesis, you use a less than bracket and a greater than bracket. And everybody will understand that that's the x component and the y component. Stuff a unit of newtons in here, but anyway, I apologize for that being so small. The C vector, so in this case, we see C is a y component is positive, the x component is negative. The angle right here is 53.1. So when I take the sine, I get this side over the hypotenuse. When I take the cosine, I get the y over hypotenuse. So cosine is going to give me the y component this time, and sine is going to give me the x component. The magnitude of it was 25.00 newtons. So C sub x is going to be 25.00 newtons. times, in this case, like I said, it's cosine 53.1 degrees. Again, that's that special 3, 4, 5 triangle that we're talking about. Oh, this is C sub x. Oops, I drew the wrong one. C sub x is 25.00 newtons times the sine of 53.1 degrees. Remember, the 53.1 is the bigger side, and this is across from it, so that's got to be the bigger of the 3, 4. So it's going to be the 40 or the 4. But notice this 25 is not 5; it's 5 times 5. So I got to multiply the 4 that would be here by 5. So I end up getting negative 20 newtons for this one. Again, I got to force that negative. And then I'll go ahead and do CY down here since I made a mistake. That's going to be 25.00 newtons. And that's going to be multiplied by the cosine of 53.1 degrees. The cosine of 53.1, remember the 53.1 is opposite the bigger side because that's the bigger angle. So that means this is the smaller side, so this should be 3. But this 25 was 5 times 5, so this must be 5 times 3, or in this case, positive 15.00 newtons. So we could say that C is actually equal to, I'm going to do that other notation again since I messed up on the units looking so bad before. It's going to be negative 20.00 newtons, comma, 15.00 newtons greater than. So there's my C vector. And now all I have to do is my D vector, and then I can go ahead and add all these components to get the new X and new Y component of R. So the D sub X, notice D sub X is a negative component, and it's opposite the 60-degree angle, so we're going to use sine for it. So I'm going to say 40.00 newtons times the sine of 60 degrees. Since it's opposite, remember 60 is opposite the big side, so that's the square root of 3 over here, and the other one will be the 1 side. So we got 40 newtons times the sine of 60, and that has to be negative, so I'm going to force that, and I put a negative right there. And when I actually do this, I realize that 40 is not quite 2. Remember, the 60, 30, 90 triangle has a hypotenuse of 2. So this is obviously measured by 20, or multiplied by 20. So I've got to take the 1 that I would otherwise have for the opposite side. This would be square root of 3. And for the adjacent side, the 60 degree right there would suggest that this is the small side. This would be the 1. This should be the square root of 3. So when I do that, I get 20 times the square root of 3, which is about negative 17.32 would be 10 times, and then 2 times that would be about 34.64. So it's negative 34.64 newtons. And then the y component, dy, is equal to, again, negative, so I'll force that, 40.00 newtons. And that's times the cosine of 60 degrees. Now the cosine of 60, you can see that's the smaller side, so that's the 1. But I had to multiply the 2 by 20 to get this, so I have to multiply the 1 by 20. So this gives me negative 20.00 newtons. So I can write the D vector as negative 34.64 newtons in the I hat direction, minus 20.00 newtons in the J hat direction. Now all I have to do is just add the like components. So you can see I take the X component of A, that's 10. I take the X component of B, that's 17.32, so I'm up to 27.32. And then I take the X component of C, that's negative 20. So I was up to 27.32, and now I'm down 20 from that, so I'm up to 7.32. And then I got to subtract from that 34.64, ultimately that's going to give me 20. That's going to give me, actually I thought I had worked that out already. That's going to give me 34.64. No, well, let's do it with our calculator just to be safe. So I'm going to do 10 plus 17.32 plus negative 20 for the C, and then plus negative 34.64. Now I add all those up, and I get negative 27.32. So R sub X is negative 27.32 newtons. And then when I add up the Y components, I get 10 for this one. I get negative 10 for this one, so that's why that one was so close to the x-axis. It probably should have been exactly on it, but I made a little bit of an error with drawing it, so that's not bad. It just happens. And then 15, positive again. Make sure that's right for positive. Yeah, that's the Y component. It should have been positive. And then negative 20. Okay, now I'm going to add these. And I get negative 5. I'm going to use a different notation this time so I can complete my claim of this being the perfect vector problem. And this will be minus 5.00 newtons in the y hat direction. So that's another thing you can use. You can use x hat and y hat instead of I hat and j hat. So then it'd be I hat, j hat, k hat, or x hat, y hat, z hat. So those are all good. That is now my actual resultant vector. But how good is that? I mean, how good is these two? Does this actually compare? Well, the way we have to do this is we now take this thing and represent it as a vector. So it's obviously going to have 27.32 in the negative x direction. So I'm going to say, that's about right. Okay, in other words, it really doesn't matter. I'm just trying to get a rough estimate of what quadrant it would be in. And then I'm going to go down 5. Well, this is about 5 times as big as 5. So I should draw the 5 times quite small. So this is 5.00, and this is 27.32. And then that means my resultant vector R is this guy, and the angle is this guy. So R is going to equal the square root of 27.32 newtons squared, using the Pythagorean theorem, plus 5.00 newtons. Notice I didn't care about the negatives because I'm squaring it and it doesn't matter. Now when I take the sum of the squares of those two, double check my math, 27.32 squared. And 5 squared, take the square root, I get 27.77. Newtons. Not too bad. I'd come up with 27.55. The angle, on the other hand, I'm going to use my inverse tangent. So theta is going to be the tangent inverse of the opposite, which is 5 over the hypotenuse, which is 27.32 newtons. And when I do that, 5, 27.32 divided by, now do inverse tangent, or arctan, depending, and I get roughly 10.3 degrees, 10.4 degrees. So according to the math, R should actually be, and this is actually the correct answer, though the graphical is an approximation. So the R should actually be 27.77 newtons at 190.4 degrees. So if you try that out, what you're going to find out is basically that magnitude is off by about 0.7%, and that direction's on the order of a less than 1% as well. So my approximation, doing it with the actual math, is not that much more precise. I mean, it's actually 100% correct, but the graphical way is not that much imprecise. So that's how you add vectors. Specifically, that's how you add them graphically. I just connected them, put the tail of the first one down, and then drew another coordinate system at the head of the first one, and then drew the second one, and then drew another coordinate system at the head of the second one, and then drew the third one, and then drew another coordinate system at the head of the third one, and then drew the fourth vector at the head of the first one, and then the head of the last one, of course, is the end. So I go from the origin where I started, draw a vector to that. That's my resultant. I was able to measure the angle. I was off by on the order of 1%, and I was able to measure the distance, and then of course use the scale, 10 newtons equals 2 centimeters, to get it back to 27.55. This was 27.55 graphically. What we had mathematically and correctly was 27.77 and 189 here versus 27, or excuse me, and 190, whereas here I had 27.55 and 189. So if you're actually using 189 as opposed to 9 and 10, you're using 189 and 190, then it's well under 1%. But the main point is the graphical way does work quite well. I hope that helps.